Okay, this is the mark scheme for the Year 12 waves test. We'll start with some multiple choice questions. So which of the following waves cannot be polarised? So you can polarise transverse waves, you can't polarise longitudinal waves, so we're looking for a longitudinal wave. Right, radio waves, microwaves and ultraviolet waves are all electromagnetic waves which are transverse. So the only one we can't polarise is the sound wave. So that is the ultrasonic wave B. The frequency of the first harmonic of a standing wave on a wire is F. The length of the wire and the tension of the wire are both doubled. What is the frequency of the first harmonic as a result? So we need to look at the formula. F equals 1 over 2L times root T over mu. So that's this F, and now we need our new F, F dash, and this is 1 over 2 lots of 2L times the square root of 2 over mu, which if we take out the 1 over, so this is our F, to get that the same we have to take the root 2 out and the 2, so hopefully you can see those two are the same. This gives us root 2 over 2, but root 2 over 2 of course, if you just think about your maths, is root 2 over root 2 times root 2, which is 1 over root 2. So our new frequency, F dash, is our old frequency divided by root 2, which is A. Question 3. 2 points in a progressive wave are 1/8 of a wavelength apart, so this is 1/8 lambda over 8, and the distance is 0.5 meters. So lambda over 8 is 0.5, which means lambda is 4 meters, and then C equals F lambda is 10 hertz times 4 meters, which is 40 meters per second. So the answer is C. Okay, number 4. So which of the following is correct when total internal reflection occurs? I always like to draw myself a little diagram first with a semicircular block and total internal reflection, where this angle has got to be more than the critical angle. So the angle of incidence is less than the critical angle. No, that's wrong, because this angle has got to be more than the critical angle. The light meets an optically less dense medium, so we are going from glass into air normally, so glass to air in this case is an optically less dense medium, so I like that one. The light enters a medium with a higher refractive index. Well, that is the opposite of the one before, so that's not correct. It's going from glass to air. That's got a lower refractive index. The angles that the incident and refracted rays make with a normal are the same. Well, there is no refracted ray. This is the reflected ray. The angles are the same, but this is refracted, so not that one. Question 5. What is the speed of light in glass with a refractive index of 1.42? Well, you need to understand that the definition of refractive index is that the refractive index is the ratio of the speed in light, the speed of light in a vacuum divided by the speed of light in a substance. So the speed of light in a substance is the speed of light in a vacuum divided by the refractive index. That's 3 times 10 to the 8 divided by 1.42, and that comes to 2.1 times 10 to the 8, which is B. Okay, number 6, quite complicated this one. So electrons and protons in two beams are travelling at the same speed. The beams are diffracted by objects of the same size. So which correctly compares the de Broglie wavelength lambda E of the electrons and the de Broglie wavelength lambda P of the protons? So let's do this part first. So the comparison of the de Broglie wavelength, we need to remember the formula that lambda equals h over mv. So the mass of the electron is a smaller number, so the lambda is bigger, so lambda E is greater than lambda P. And that means it could be A, but it's not B, it could be C, but it's not D. Then we need to look for the diffraction pattern. Well, this one is sine theta equals lambda over B. So if the lambda is bigger, the diffraction pattern will be wider, so the electron beam width will be wider than the proton beam width, because lambda E is greater than lambda P. So the correct answer is A. Okay, the last of the multiple choice questions. So in a diffraction grating experiment, the maxima are produced on a screen, which causes the separation of the maxima of the diffraction pattern to decrease. So we're on a diffraction grating, so n lambda equals d sine theta. So sine theta equals n lambda over d. So we're looking for sine theta to decrease, which means that, theta to decrease, which means that sine theta has got to also decrease. So using the light with a longer wavelength, the wavelength's on the top here, so a bigger wavelength is going to mean a bigger angle, so not that one. Increase in the distance between the screen and the grating, well that's not in the equation, but if we're doing this, and here are our diffraction maxima, and this distance is increased, then this is also going to increase the diffraction spacings. Increase in the distance between the source and the grating, well this is irrelevant, okay, this is here, I put my laser over here, so that's this distance, but that's neither here nor there, the beam just carries on. So using a grating with a greater slit separation, so now we're making D bigger. If D is bigger, then sine theta will become smaller, theta will become smaller. So D is the correct answer. Okay, so question 8. So a piano string has a tension of 681 newtons, vibrates with a fundamental frequency, so this is what we now call only the first harmonic, so stick with that name, of 92.5 Hertz, and has a mass per unit length of 1.87 times 10 to the minus 2 kilograms per meter. Calculate the length of the string. So it's this equation again, F equals 1 over 2L times the square root of T over mu, mu being the mass per unit length of the string. So we can put the numbers in. 92.5 is 1 over 2L times the square root of 681 divided by 1.87 times 10 to the minus 2. And you can work that out first if you like, or you can do the algebra. If you do the algebra way, you'll get L equals the square root of 681 over 1.87 times 10 to the minus 2 divided by 92.5 times 2, because the 2L would have gone up there, and I've divided by the 2, and that gives us 1.03 meters. 3 significant figures, the same as the data in the question. On the figure below, it shows a string stretched between 2 fixed ends. Draw on the figure what we are now calling the second harmonic. So the first harmonic, don't draw this on, but just to show you, the first harmonic is this one. So the second harmonic is where we've got one node in the middle. So you need to be mark that in so you get it roughly right. Okay, there's our second harmonic. Okay, state how you could make a string on a stringed instrument vibrate in this mode of vibration. So if you just pluck the string in the middle, it's going to vibrate in this dashed line. So if you want to make it vibrate in this mode, the thing to do is just loosely hold the center. So loosely hold the center and pluck at the 1/4 or 3/4. So we're plucking it here or here to make it vibrate in that mode. Okay, describe how you would investigate the variation of the fundamental frequency, or the first harmonic as we know it now, of the string with its length. So what variables would you control and how would you do so? And we might draw a diagram if we feel the need. Okay, so think about what you're going to change and what you're going to measure and what you've got to keep the same. So we're changing the length, so we need to vary the length, and possibly we would have some sort of setting with a weight over the end on a pulley, and we could change the length L here, and then we would need a way of measuring the frequency. So measure the frequency, possibly with a microphone and oscilloscope, and we would need to keep the mass per unit length, and the tension would be kept constant, and then we would need to know what to do when we've got the results. So we would plot a graph, and the answer is never going to be plot a graph and just stop there. What graph are we plotting? So we could plot a graph of the frequency against 1 over the length. Because it's this equation, f equals 1 over 2l root t over mu, we know that the frequency is inverse proportional to length, so frequency against 1 over length should give us a straight line going through the origin, a proportional relationship. Okay, question 9. So diamond jewels sparkle because the light that enters the diamond at different angles is reflected back to an observer. Figure 1 shows the path of one of these incident rays through a diamond. So we've got a ray coming in, so the light shining on the diamond, it reflects around inside the diamond and comes back out. This is why diamonds are sparkling. So calculate the critical angle for diamond. So this is sine theta c is n2 over n1. So the critical angle occurs when the light is leaving the diamond, so n2 is 1, n1 is the medium we're in, which is 2.42, and the inverse sine of 1 over 2.42, which is 24.4 degrees. So if this angle, for example, is above 24.4 degrees, then the light will be internally reflected. The ray shown in figure 1 enters at an angle of 50.2 degrees. Calculate the angle of refraction theta. Well, this is nothing to do with total internal reflection yet. We're going from the air into the diamond. So this is n1 sine theta 1 equals n2 sine theta 2. So n1 is now the air. So 1 times sine 50.2 equals 2.42 times sine theta 2. So theta 2 equals the inverse sine of sine 50.2 divided by 2.42. And that is 18.5 degrees. Always have that little check. They've helped you out on the diagram here. You can see the angle of refraction is smaller than the angle of incidence. If you do this wrong, you'll get an angle of bigger than 50.2 degrees. But we know we're okay there. So 18.5 degrees is a sensible answer. Okay, so cutting diamonds is a highly skilled profession, and it is done to make them as sparkly as possible. So the angles of the diamond are chosen to maximise the amount of light reflected. Figure 2 shows a diamond with different angles to that of a normally shaped diamond. The dotted lines show the normal shape of a diamond, so don't be confused here by these dotted lines. They're just to show you the shape of the diamond in the previous part. This is an alternative way to cut a diamond with this longer sort of V down here. Draw on figure 2 the path of the ray until it leaves the diamond. So if we follow this line down, as I say, ignoring that dotted line which isn't there to do anything at all, the light comes down to there, and then you can see there's a very large angle of incidence. So they're not expecting to get a protractor out here. They're just expecting you to do this by eye. So make those angles reasonably similar. So about like that. And then the key thing here is you need to draw another normal. This angle clearly is less than the angle, the critical angle. So this light will be refracted, and it will be refracted away from the normal. You have to draw that normal in so that you can get that right. So somewhere around there. And then moissanite is a transparent material with a refractive index of 2.67. So let's remind ourselves diamond is 2.42. So discuss whether this material, if made of diamond in the shape shown in figure 1, would reflect more back more or less light than the diamond. So this is a bigger refractive index, which will give you a smaller critical angle. If you've got a smaller critical angle, then the light is more likely to be reflected. So the new material is going to reflect more light. So it turns out moissanite is a girl's best friend. So figure 3 shows an infrared ray entering an optical fibre. The refractive index of the core is 1.55 at infrared frequencies, so that's just reminding you that the refractive index isn't a constant for material, even though we often treat it as if it is. It does depend on the wavelength or the frequency. Here's a diagram of the light entering the fibre. Calculate the speed of which it travels in the core. So again, we're back to the C in the material is C in a vacuum divided by the refractive index. That is 3 times 10 to the 8 divided by 1.55, and that comes to 1.94 times 10 to the 8 meters per second. The wavelength of this infrared radiation is 300 nanometers in the air. Calculate the wavelength in the core. Well, what we need to understand about this is, if you remember C equals F lambda, the speed changes, the wavelength changes, but the frequency stays the same. So if we take C over lambda in a vacuum and C in the substance over the lambda in the substance, those two will both be equal to the frequency, and the frequency doesn't change. So we've got 3 times 10 to the 8 divided by 1300 times 10 to the minus 9 equals 1.94 times 10 to the 8 over the lambda in the substance. And okay, so that gives us lambda s equals 1.94 times 10 to the 8 over 3 times 10 to the 8 times 1300 times 10 to the minus 9, and that gives us 841 times 10 to the minus 9, or 8.41 times 10 to the minus 7, because they want the answer in meters. State one reason for surrounding the core with cladding. You can have about not scratching the core, that kind of stuff, but I think the best answer is that it increases the critical angle, and the reason you want to increase the critical angle is that reduces modal dispersion. It means the light has to follow a line reasonably close to the axis of the fibre, and therefore you don't get spreading of the light from the light that's reflecting at this kind of angle and taking a lot longer to travel down the fibre. Okay, question 10. The diagram shows a Young's double slit experiment performed with a tungsten filament lamp as the light source. So we've got our light source over here, a single slit, a double slit, and then the screen over here with a graph over here to show us the intensity of the light as it hits that screen. On the axes in the diagram above, sketch the graph to show how the intensity varies with position for a monochromatic light source. So even though it said a tungsten filament which will give us white light, this is talking about a monochromatic light source. We will get a central maximum, and then we will get maxima on either sides which are equally spaced. So as ever, I would draw myself some dots, because it's very difficult to get the pattern right if you don't have a few guides to help you draw the curve. So it's got to go through those points. These are equally spaced. You can make the intensity descend a little bit, because remember that each one of these slits is a single slit itself, so it will create its own pattern. But normally over the central area, these are roughly equally bright, and then draw them in as curves. And you'll see hopefully that if you've done the dots to guide you, that these distances stay the same. So these are fringes, okay, fading away and coming back, of equal width. For an interference pattern to be observed, the light has to be emitted by two coherent sources. Explain what is meant by coherent sources. So the common mistake here is to write that they are in phase. They don't have to be in phase, they have to have a constant phase difference. Now of course normally what we have is they're in phase and the constant is 0, but they don't have to be. Sometimes the exam board like you to write that they have to have the same frequency, but to my mind you can't have a constant phase difference unless you're the same frequency. Explain how the use of a single slit in the arrangement above makes the light from the two slits sufficiently coherent for fringes to be observed. So the key thing to understand here is the light is travelling through the single slit, it's diffracting as it goes through that slit, and then these two sources are therefore in phase, or if the distances aren't quite the same, at least they're still coherent. So the light diffracts at the single slit, and spreads to both of the double slits. Okay, in this experiment light behaves as a wave, because of course this was the experiment that convinced people that light was a wave. Explain how the bright fringes are formed. So the key thing here is that there is a diffraction pattern from each of the double slits these overlap and superposition occurs. That's how the pattern is formed, but because they're asking for the bright fringes, so bright fringes are formed where there is constructive interference. Okay, so cover up one mistake here. So scientist carries out the Young double slit experiment using a laser that emits a violet light of wavelength 405 nanometers. Separation of the slit is 5 times 10 to minus 5 meters. Using a meter rule, the scientist measures the separation of two adjacent bright fringes to be 4 millimeters. Calculate the distance between the double slits and the screen. So the equation on your data sheet is W equals lambda D over S. We have got lambda is 405 times 10 to the minus 9 meters. We've got S equals 5 times 10 to the minus 5 meters. And we have got W equals 4 times 10 to the minus 3 meters. Okay, powers of 10, there's obviously lots of traps that they've laid for you there. So D equals WS over lambda, which is 4 times 10 to the minus 3 times 5 times 10 to the minus 5 divided by 405 times 10 to the minus 9. And if you do that, it comes to 0.49 meters. Describe the change to the pattern seen on the screen when a violet laser is placed by a green laser. So what we need to know is that the wavelength of green is bigger than the wavelength of violet. And what that means is, if we go back to the equation, W equals lambda D over S. It is only a described question here, so we don't need to explain why this is. But if W equals lambda D over S, if we make lambda bigger, W will be bigger. So the fringe spacing will increase. Okay, it's only a 1 mark question, so we don't need any more detail than that. So the scientist uses the same apparatus to measure the wavelength of visible electromagnetic radiation emitted by another laser. Describe how he should change the way the apparatus is arranged and used in order to obtain an accurate value for the wavelength. So if you look back to what we've got at the moment, there's a couple of key little clues they've given you. We had D was 0.49 meters, which is quite a short distance really for D. If we did it in class, we probably did about 3 meters. And also in the previous question, they told you W was measured as 4 millimeters. And again, we wouldn't have measured the fringe separation for one pair of fringes because we've got lots of fringes to look at. So the key 2 clues they've given you about how to do this accurately, they've emphasised the word accurate here, is to increase D, which will increase W, and to measure measure across a large number of fringes and calculate the average spacing. I say the average spacing, although obviously of course all the spacings are the same. Okay, in question 11, so the diagram below shows the paths of microwaves from 2 narrow slits acting as coherent sources through a vacuum to detector. So the first thing to understand maybe on this diagram is that the waves are going this way, so this is not producing the waves, this is detecting the waves. They've come from down here and they're meeting at that point, and we need to understand what's going on there. So the frequency of the microwaves is 9.4 gigahertz. Calculate the wavelength. So this is just a C equals F lambda. So we are doing the wavelength is the speed divided by the frequency. These are electromagnetic waves, so it's 3 times 10 to the 8 divided by 9.4 times 10 to the 9, and that gives you 3.2 times 10 to the minus 2 meters. So 3.2 times 10 to the minus 2 meters. If you just have a little think about that, that's 3.2 centimeters. That's kind of what we expect for wavelength of microwaves. 2.8 centimeters is the standard. So they've just changed that number slightly. So using the diagram above and your answer to part A1, calculate the path difference between the 2 waves. So we need to look on this diagram and just simply count that is 1, 2, 3, 4, 5, 6 waves is the path from there, and this is 1, 2, 3, 4, 5 waves from there. So the path difference is 1 times the wavelength. So that is also 3.2 times 10 to the minus 2 meters. State and explain whether a maximum or minimum is detected. So this is a state and explain. So it's a maximum. Why is it a maximum? Because the path difference is a whole number of wavelengths. A whole number of wavelengths. And why does that make a maximum? Because constructive interference. Sorry, I've lost the ability to write. Interference occurs. The experiment is now rearranged. The perpendicular distance from the slit to the detector is 0.42 meters, and the interference fringe spacing changes to 0.11 meters. Calculate the slit separation. Give your answer to an appropriate number of significant figures. I just write down SF down here now, just to remind myself that when I get to the answer I have to, for the third mark, it's a shame to lose that mark to do that. So W equals lambda d over S. We want the slit separation, so we want S is lambda d over W. The wavelength hasn't changed, we're just rearranging the experiment. So the wavelength is still 3.2 times 10 to the minus 2. The distance is now 0.42 meters, and the fringe spacing is 0.11 meters. And if you put that in your calculator, you get 0.1218, but an appropriate number of significant figures. All the data is to 2 significant figures, so 0.12 meters. Okay, with the detector at the position of a maximum, the frequency of the microwaves is now doubled. Again, we're on a state and explain, which is why it's 3 marks. State and explain would now be detected by the detector in the same position. So key things are here: if we double the frequency, so doubling the frequency halves the wavelength. So what we knew before was that we had a whole number of wavelengths, path difference, i.e. that's an n. So now we've halved the wavelength, the new path difference will be 2n, but that's still a whole number, so still a maximum intensity.